So in this problem, we want to find the maximum positive moment that can be developed here at C, which is the center of this span. And we've got a single concentrated live load. Live means it's moving around. We've got a uniform live load. That's something a little new. We'll talk about that. And then we've got our dead load. We've already seen something like that. So the first step is I want to construct the influence line for the moment at C. So what does that say? Well, Mueller-Breslau tells me I can go to C and I can imagine a connection that has no moment. That would be a hinge. And then on that structure, I will apply positive bending moments. How will that structure move? Will point C move up or down? It will move up. So with that as my qualitative value for the shape, I can now say that the moment at C, as the unit load varies over the structure, give me a second to draw these lines down. What will happen? Well, if this point moves up, say to here, what happens on the left side? Well, it's attached at A, so it's going to have to bend and pivot back down. What's going to happen on the right side? Well, if this point moves up, it'll seesaw over B, and the free end will go down. So there's my qualitative shape for my influence line. And just remember that this is 4 feet, this is 4 feet, and this is 4 feet. So if I were to determine this height of my influence line, what would the value here be? It'd be that value but minus, because these are similar triangles, they have the same base, so the heights would be equal. Now how do I find the height, or how do I find this value of the moment? Well, that would be the moment at C when what is true? When the unit load is there at 4 feet. So I have to solve one problem that looks like this. So I have a pin, I have a roller, and now the problem I want to solve is when the unit load is at 4 feet, which is right here. And what am I trying to find? The moment at C, which is right where the load is. So if I cut this structure here to find the moment at C, do you want to work the left side or the right side? I think the left side is a good choice. So we'll work the left side. And if I work the left side, what do I need? Reaction at A. How do I find the reaction at A? I can do that, or I can also do what? Can I draw the influence line for the reaction at A using Mueller-Breslau and figure out the equation? Could. But I think it's going to be just as easy to do what? How do I find the reaction at A for this position of the load? It's not going to move. It's at that point. Sum at where? B. Make sure it's in equilibrium. So what's the distance from B to there? 4 feet. So that would be 1 times 4 feet. That creates positive moment. AY creates what kind of moment about B? Negative. And what's the distance from B to A? 8. So what's AY equal to? 1/2. Is that surprising? Shouldn't be. I've got a simple supported beam with a load of 1 in the middle. What do you expect the reaction to be? Half. BY would be 1/2. Now, right now, remember, the load's not moving. We're not trying to find the influence line for AY. We're trying to find what? AY when the load is right there. So now that I know AY, I can cut my structure at C I know AY is 1/2. And now I'm looking for the internal moment at C. And whether you decide to include the 1 or not, it doesn't matter, because what's the moment arm from the cut to 1? 0. It's not going to create any moment. So what does create moment about C? The reaction. So if I sum moments using right-hand rule for my signs about the cut I just made, make sure it's in equilibrium, what do I have? If I've got my internal moment, what's that, positive or negative? Positive. And then what kind of moment does the 1/2 create about C? Negative. So the force is 1/2 and the distance is 4. So the moment at C is 2. And it'll have units of feet. So this will have units of feet, and I now know this is 2. So similar triangles tells me this is -2. So what do you think? So once you did the qualitative part with Mueller-Breslau, you really ended up with a pretty simple problem. If I gave you this problem on the exam, hey, here's a beam with a load of 1 in the middle, what's the moment at C? You should get a really big smile on your face, because that's going to be the easiest exam problem you've ever had.
It's going to be on the test, right?
But now it's just what? A part of this problem. So that allowed you to put values on here, and then similar triangles let you determine that this. So now I've got a fully enumerated influence line for the moment at C. Now I solved the problem. What is the problem? I have a unit load, live unit load, dead unit load, and a concentrated force. So let's start with the concentrated force. Oh, by the way, I want to find the positive moment, right? So if I start with first the concentrated force, and oh, by the way, this is a live force, it's moving around. It has a value of 8 kips. So where should my 8 kip force be that I create the maximum moment at C? Should it be here? Well, that would be a maximum negative value, right? Should it be here? No, that creates no moment. So it should be here. That's the maximum value. What is the maximum value? 2 feet. So I'll multiply it by 2 feet. So this moment is equal to what? 16 kip feet. Let's do the uniform dead load. Uniform dead load has a value of 1 kip foot. So I know the load is going to be 1 kip per foot. Now remember, when we do uniformly distributed loads, we have to take the area under the influence line. Now dead load, you can't control. It goes over the whole structure. So I have to take the total area under this curve. There's a positive piece and there's a negative piece. So I'll do the first positive piece. They're both triangles. So I'm going to multiply it by the triangle, and it's going to be 1/2 base. The base is 8 feet, and the height is 2 feet. So that's the area of this triangle here. What's the area of this triangle? 1/2 base, 4 feet, times height, minus 2 feet. So that's 4, that's 8, so that's 4. This would be 4 kip feet. Is that right? Did I do that too fast?
When you said 4, I thought I was like, oh, wait, it's -4.
Yeah, so this is 8 plus -4 is 4. 4 times 1, so it should be 4 kip feet. Okay? Now this is something a little different. So this is going to be the uniform load. But this one is live. So this uniform load can vary where it is applied to the structure. It doesn't go across the whole structure. Where should I put a uniform load to create the maximum positive moment? Should I put it over here? No, because I'm going to multiply it by a negative area. I'm going to put it over the first 8 feet because it's all positive area. So that value is 3 kips per foot. And this time I'm only going to multiply it by the positive area because I'm looking for the positive moment. So that'll be 1/2 base, which is 8 feet, times the height, which is 2 feet. And that's 24 kip feet. So what's the total moment at C? I add these together. So 16 plus 4 plus 24. That's 44. So now that's the maximum. Sorry? 40?
No, it's 40.
Oh, with the 4.
Did I miss something?
My bad. I just did 16.
So that's the maximum moment caused by this loading. So let's see what that loading looks like. So what that would look like.
All 3 of those added together?
Oh yeah. Because I have 3 different loads, right? They're all happening at the same time. So this is what I've got. I've got my roller. And I've got my pin. So first thing I'll do is I'll color code these. So let's do the uniform dead load in blue. So that's going to go across the whole structure. So there's my dead load. And that was 1 kip per foot. Let's do the live load. I'll do that in orange. The live load only goes over the first 8 feet, which is here. And that live load is a little bit bigger. It was 3 kips per foot. And then where did my concentrated load go? Right here. And that's 8 kips. Purple. So that's the combination of loads and locations that creates the maximum positive moment at C. What do you think of that? Pretty cool, huh? So what would this be? This could be, the dead load would be maybe the weight of the deck on a bridge. And this might be a wheel load that can be anywhere it wants to be. And this could be some representation of, say, the truck load, which could be anywhere it wants to be. So this is the position of those 2 things that creates the maximum moment at C.
And then that AK is just someone standing on it? Or a truck? Wait. What's the AK represented in that example?
What are you saying?
The 8 kip point?
That's the value of the load. It was given as 8 kips.
Okay.
So if it was given as 20 kips, it would be 20.
In the example of the bridge.
Oh, I don't know. That would be maybe a 1-wheel load.
Dr. Campbell,
Yes.
The uniform live load, when we multiply it by the area under, it's the area under the maximum.
Just the positive area.
moment.
Just the positive areas. If I want the positive effect, I would just use the positive area. If we had a really complicated line, you maybe have a positive area here and a positive area here, then you'd take all the positive areas. Okay. If you want the negative effect, you would just do it over the negative area. So what would change? For the dead load, I can't change. Where would my live uniform load shift if I wanted to try to make the biggest negative component? It would just be over the last 4 feet. And where would my point load go for negative? All the way to the end. I have a different scenario, and I'd get a different value, but I'd get a negative moment. It'd be the largest negative moment. Okay.